Let's look at some synthesis problems using electrophilic aromatic substitution or potentially nucleophilic aromatic substitution. In this case, we have a tri-substituted benzene ring, and we have three substituents on, all of which are deactivating groups. The chlorine, though, is an ortho-para director, and so we can notice that there are no groups ortho-para to the chlorine. And because the chlorine is the weak deactivator versus the moderate deactivator versus the strong deactivator, if we had the chlorine on before either of these two substituents, they would add ortho or para to the chlorine. So that tells me that the chlorine needs to be added last, because otherwise I would get something added ortho-para to the chlorine, and I don't see that. So I need to add the chlorine in my final step. Okay, so now my target is this di-substituted ring. Again, I have both metadirectors and deactivating groups, so I can either do Friedel-Crafts acylation of nitrobenzene to put this group on, or I can nitrate the ketone with the aromatic ring. Now remember that the limitations with Friedel-Crafts acylation are that they cannot occur when the ring is moderately or strongly deactivated. So it is not possible to make this bond with the nitro group already installed. So that means I should install the nitro group after the ketone. Now I have a mono-substituted ring, and it's pretty straightforward to get there from my starting material. All I need to do is choose the appropriate acyl chloride and aluminum trichloride for Friedel-Crafts acylation. So this was pretty straightforward. We didn't have to change any of the groups once they're installed. We just had to decipher the correct order in which to add these groups. Let's look at another example. So here we have a ring that has three groups on them. Two of them are carboxylic acid functional groups, which is maybe strange given what we just learned in this chapter. We didn't learn anything about adding carboxylic acid functional groups, but we did learn how to make a carboxylic acid functional group on an aromatic ring in the Aromatics chapter. And so chances are we need to use that strategy, taking an alkyl group in these positions and oxidizing them using our sodium dichromate oxidizing reagent to turn them into carboxylic acid functional groups. Also remember that, again, installing this ketone via a Friedel-Crafts acylation when we already have these strongly deactivating groups installed is not going to work. So most likely we do the oxidation of the alkyl groups as a final step. And we'll just put methyl groups here because we know that we're going to lose every carbon except for the one in the benzylic position. So there's really no reason to put on a whole bunch of carbons. And so let's look at this target. Could I install the acyl group from 1,4-dimethylbenzene? And I think I could. These are both activating groups. They will both direct ortho-para, so they're kind of in conflict with each other. But really each one of these four positions on the ring now, because we would have a highly symmetrical ring, would be equivalent. So I think it should be no problem to do this Friedel-Crafts acylation from dimethylbenzene. And thus getting to dimethylbenzene is rather straightforward. We just need to methylate twice. And we could show two steps if we wanted to. Basically repeat what we exactly just did. Or we might say excess methyl chloride. That would probably work as well. Although we'd have to be careful that we're not adding more than two methyl groups here, because we only want the 1,4-dimethylbenzene, not multiple triple and quadruple methyl groups added to this molecule. So here we see that we've combined both electrophilic aromatic substitution twice, and then we've combined a reaction from the aromatics chapter where we can, as long as there is one hydrogen in the benzylic position, we can use this to oxidize any alkyl chains to the carboxylic acid. And you'll notice we did not affect the ketone because there are no hydrogens here in the benzylic position. Also, the ketone is the fully oxidized version of any sort of oxygen species at this carbon, so there's no danger of over-oxidizing at this position. Let's look at one more. In this example, we have two ortho-para directors, and yet nothing on our ring is ortho or para from another substituent. So that's a pretty big clue that at some point one of these, or maybe both, would have to have been modified to change them from a meta-director to the current ortho-para directors. And we know that there are a couple options here. We can have an NO2 group that gets modified to make an NH2 group. And of course the NO2 group is a meta-director. Or we could have a acyl chain, which is also a meta-director hanging off the ring. We can modify that to make a alkyl chain that turns into an ortho-para director. So the way to do this is actually reducing both of these groups using Clemmensen reduction conditions. So basically zinc, mercury, HCl, followed by NaOH, because the HCl step will protonate this base. And so if we want to free amine here instead of the NH3+, we need to use this basic workup to get rid of the extra acid that will have protonated our amine. And so we can do that and essentially come up with this intermediate via Clemmensen reduction. We could turn the NO2 into an NH2, and we can remove the carbonyl, leaving us with just an alkyl chain. So now the question becomes, which of these do I install first? Remember that Friedel-Crafts acylation cannot occur on a strongly deactivated ring, like this one would be if it were nitrobenzene. So chances are we have to install the acyl group first, then we can nitrate to put the nitro group in the meta position. So nitration conditions, H2SO4, HNO3. Starting from the acyl benzene, we can then nitrate that to make the meta-nitro acyl benzene, and then we can reduce both functional groups at the same time to get our desired product. And thus getting from benzene to the acyl benzene is pretty straightforward. We just need the required acid chloride. That's 4 carbons, 1, 2, 3, 4. It's good to make sure that you don't get losing a carbon. And then AlCl3 as our catalyst. So this is a nice 3-step synthesis to make the aminobenzene with an alkyl side chain. Okay, one more example. This setup looks a bit weird at first. Like we got benzene and then we got this long chain thing with a substituent. Remember that phenyl is an abbreviation for benzene. So we have our benzene ring here. It's just disguised as an abbreviation right here. So what I'm doing here is somehow adding a side chain to the benzene and ending up with a vinyl group or an alkene next to the ring. So this is some clues here tell me that we're going to have to remember how to make alkenes, and that's from organic semester 1. And somehow we have to make a carbon chain on our benzene ring that gives us the opportunity then to manipulate some functional group in one of these positions to make the alkene. Alkenes come from a number of potential precursors, so it's helpful here to draw those out. And I'm going to put the ring there just so I can keep track of it. Most likely, though, we have some leaving group at this position, which we could then eliminate using an E1 or E2 reaction to form the alkene. So if we have a leaving group there, how do we get that leaving group? Let's just say that it is a chloride. And we'll use a strong nucleophile, strong base. This is a tertiary chloride. We should have E2, no problem. And this is the E version, so that should be favored in this case right here. So how do we get a chloride there? And how do I make this bond? I can think of a couple different ways to make that bond, but most likely we're going to have to functionalize the aromatic ring, turn it into a nucleophile, and then make that bond. So there's a couple options. We could look at it as synthesizing an alcohol and creating this bond, and we learned how to create that bond in the alcohol chapter. That would be from a Grignard reaction. So mix those two together, followed by mild acid workup, and we get that tertiary alcohol. Another way to make that bond would be from the acid chloride plus benzene. And that would lead us to a ketone. And we could add a methyl group and turn that into a chloride in 2 steps by using a Grignard, so methyl Grignard, and then taking the resulting tertiary alcohol and turning that into the tertiary chloride. That's quite a few steps. I think it's probably easier to make this Grignard from benzene, which really just requires Br2, FeBr3, and then magnesium and ether to create the phenyl Grignard. Now I have my good nucleophile, and I used an electrophilic aromatic substitution step to add a bromine to the ring. Now I can turn that phenyl bromide or benzyl bromide, no, phenyl bromide, into phenyl Grignard. And then I can react the phenyl Grignard with the required ketone. Let's see here. I need to count my carbons to make sure I know how many I want to have. 1, 2, 3, 4, 5, 6. And I want the ketone to be on the second carbon. So I need a 6-carbon chain with a ketone on the second carbon. And that would be my first step. Second step would be mild acid workup. So I can protonate the O- that's formed. And of course, you remember the Grignard mechanism goes something like that. I'm not going to draw the whole thing out for you, but you can certainly do that on your own. So now I have my 2 carbons, 3, 4, 5, 6, and that is going to be the same. So this molecule here is the same as this molecule here, and now I can get to the chloride version simply by adding maybe some HCl. So I've installed the good leaving group, and then so I installed the good leaving group here. I changed the tertiary alcohol to a tertiary chloride. Then via an E2 elimination, I can make the E version of the alkene. So let me go back and number all these steps in a different color here. Let's use black. So the first step is adding a bromine to our aromatic ring. The second step is turning that into a Grignard, so I have a good nucleophile. The third step is using that Grignard to attack the appropriately shaped ketone, giving me the tertiary alcohol I have outlined in purple. The fourth step is turning my tertiary alcohol into a tertiary chloride, and then the fifth step would be elimination of that tertiary chloride to give the most substituted and most stable version, the E version of the alkene. And so you can see here that the aromatic ring appears in my product only as the phenyl ring. So this is a combination of a number of different synthetic techniques that we learned. We learned in this chapter, we learned in the alcohol chapter, we learned in the SN1 chapter back in Organic 1, and we learned in the E2 chapter also back in Organic 1. So we've combined a lot of different techniques here to affect this synthetic transformation.